This video will provide an overview of the modeling process. By the end of this video, you should understand what the steps are in the modeling process and how the modeling process is a form of a modeling tool. Now that we've covered some of the basics of modeling, I think it's important to take a step back and think about exactly what is a model. So suppose you've used R to create a model that predicts electricity demand using the temperature for the previous 3 years. I give you additional data for this year. You add the new data, you train the model again using the same features as you did before. Because you have some new data, the model parameters change a little bit, and so do the predictions. Is this a new model? And did your process for constructing the model change? Remember, the model is just a function that maps values of the features to a predicted label. The predictions are changing a little bit, so the function changed. This is a new model, but our process was exactly the same. Suppose instead, I'd given you that new year of additional data. You add that data, and going through your process, you realize that a new interaction term between some of your features improves the model forecasts. Is this a new model? And did your process for constructing the model change? Again, the predictions from this model are changing, so it's a new model. Depends on what your process was to start with. How did you determine that that new interaction term improved the model forecasts? And would you have made that same determination with the old data? Training a model is only one step in what I'll call the modeling process. This process covers the entirety of creating a forecast model. It starts with data collection and processing, your choice of loss function. It then moves on to the selection of a particular modeling tool, the selection of features, functional form, and so on. Then training the model, evaluating the model fit, and generating predictions. A modeling process is comprised of all of these steps. I'd like to think about this process graphically. Again, you'll start out the modeling process by collecting, wrangling, and understanding your data. You can't enter the modeling process without deciding what your preferences are over different types of errors, so your loss function will also enter in at this stage. Then you'll move on to a model selection process, where you're going to select features and a particular modeling tool, then train and test the model until you find your preferred version of that model. You'll use it to generate forecasts, then you'll evaluate those forecasts, and you might make additional modifications down the road. Just like in our data science workflow, the process is never complete. You should always go back and evaluate your decisions after they're made. So let's think about these steps in detail. We've thought a lot about data collection, wrangling, and processing. In terms of the modeling process, though, there are important decisions in the data wrangling process that feed into the entire modeling process. The steps that were used to collect and wrangle your underlying data, for example, did you aggregate your data? How did you do that? How did you deal with NA values in your data? What's the frequency of observation in your data? And how accurate are your data? Do your data measure information with noise, or are they very precise measures of the things you're trying to look at? Changing any of these factors can change the forecasts from a model, and therefore the value of the loss function. The choice of loss function is very important in the modeling process. Remember, the loss function is going to define what you consider to be a good model. It expresses your preferences over different types of prediction errors. So your choice of loss function should be closely aligned with your forecasting goals. Do you value accuracy or precision, or are some types of errors worse than others? Certainly, if you decide to change your loss function, you'll get completely different types of preferred models out of this modeling process. The model selection step is where you'll make many different choices about the types of information that feed into your models, selecting features, the functional form, and so on. What's going to guide these decisions? You'll want to make the choices that lead to forecasts with the lowest possible value of the loss function. But we can't just pick the model that has the lowest value of the loss function, comparing all of these choices. Why not? Because if we do that, we'll lead to models that have overfitting. These models might perform very well at making forecasts with the data we already have, but they make very bad predictions. There are ways to make these choices while minimizing the impact of overfitting. Out-of-sample validation can help there. The next step in the modeling process is to train your model. You'll do this after you make all of the modeling choices that you need to make. When training models with LM, it's quite straightforward. In most circumstances, there's a unique set of parameters that minimizes mean square error in a linear model. So two people using the same features and the same source data will always agree on the OLS model that comes out of those data. Not all modeling tools lead to a unique set of parameters. For example, a modeling tool called random forests don't lead to a unique set of parameters. Two different people using the exact same data and the exact same features might get slightly different models using random forests. This is why it's important to be specific about exactly how the model is trained. Then that end step in the modeling process is the evaluation of model fit. You're going to compute model fit using the loss function. You can't use the same data that was used when we trained the model. So what data should we use? Much like with out-of-sample validation, you'd like to use data that wasn't used as part of your previous modeling process, so you might want to set aside an additional set of data to evaluate the model fit at the end of your full modeling process. The combination of all these steps in the process defines your modeling process. You may iteratively repeat some of these steps. In particular, you might go through model selection many times to find the best model specification, the best set of features to include in your model. You may also reevaluate all of your modeling decisions as new data comes in. But this iterative process is what leads us to this modeling process flowchart. I'd like to focus a bit on the model selection process. This is a critical component of the modeling process. Here, you're going to choose the modeling tools, features, and maybe some other decisions that help you minimize the loss function. But you'd like to do all of this while still avoiding overfitting. So how might you go about doing this? Well, you could train a model, you could create forecasts, you could collect new data, or you could set aside a test sample, and then you'll compute forecast loss in the test sample. You repeat this entire process for all of the models that you'd like to consider, and you're going to prefer the model with the lowest out-of-sample loss. This is what defines this outline of the model selection process. Again, you'll divide your data into training and test samples. You're going to choose some kind of model specification. You're going to estimate that model on the training sample, use that model to generate forecasts on the test sample, and compute the value of the loss function on that test sample. Then you'll repeat with new specifications as needed, and you're going to choose the model with the lowest test sample loss. This entire process, from data collection all the way through model selection, forecasting, and evaluation, is itself a modeling tool. Why is that? We define a process ahead of time. This is going to describe the possible features and modeling tools that we're going to consider, which loss function is going to be used for evaluation, how training and test samples will be constructed, and the criteria for choosing our preferred model. All of these decisions can be embedded in our code. This process is reproducible and transparent. Two different people with the same data and the same R code implementing this entire process should get the same model at the end of the process. And that makes this entire workflow a modeling tool. In the end, after you've constructed the entire workflow, you'll provide data. Any decisions that are made along the way are documented and embodied in your R code. The result of the entire process is a single model. It's a function that translates features into predicted values of the label. This is identical to other modeling tools that we've used. It's just that the internals are more complicated. Even though this process is more complicated and embeds modeling tools inside of it, you can still think of it as a modeling tool and apply similar logic that we've used with modeling tools in the past.